Hello, everyone. In this video, we're going to begin section 8.6 in our workbook on power series. Okay, before getting started in the first example, I've just listed here some of the main goals of this section. All right, so there are three main things that we want to look at here. So first of all, recall in 8.5, our previous section, we were creating Taylor series, which are series that approximate a function. And in fact, we showed that if we look at the infinite series, that we can get spot on in some instances. But the question is then, for what values of x does that Taylor series work? In other words, which values of x does the Taylor series converge to the function value, f of x? And then kind of our second goal then, well, so for such values of x above, how many terms do we actually need in the Taylor series in order to match with our function value, or in order for that polynomial to be pretty consistent or close to our function value? And then kind of lastly, the procedure for finding Taylor series was rather involved. And so is there an easier way to find such series? All right, so those are the main topics of this section. So let's get into it by looking at example one. So example one, we're just getting ourselves reacquainted with some of the work that we did in section 8.5. So all of this in part A, you will have seen before. All right, so example one says, let P of x be the series, infinite series from n equals 0 to infinity of 2 to the n over n factorial times x to the n. This series is the Maclaurin series for the function f of x equals e to the 2x from example 1 on page 114 in our workbook. Recall Maclaurin series just means a Taylor series centered at 0. So in part A, all we need to do is write out the partial sums, p sub 2, p sub 3, p sub 4. In other words, the second, third, and fourth degree polynomials of this Maclaurin series. All right, so let's go ahead and do that. If you want to go ahead and pause the video and then just catch up and compare your work, I encourage you to do that. All right, so starting out with p sub 2. So what we're going to do is just have n start at 0 and then go from 1 and 2. So when n equals 0, we have 2 to the 0 over 0, not 2, over 0 factorial, x to the 0. When n is 1, we get 2 to the 1 over 1 factorial, x to the 1. When n is 2, we get 2 squared over 2 factorial, x squared. All right, so these aren't too bad. One thing, though, that might be odd is that we see we have a 0 factorial. So what is 0 factorial? Well, it turns out 0 factorial is defined to be 1, and this just works out for consistency and other operations that we do with factorials. So that's sort of the, maybe we could just say the definition. 0 factorial means 1. All right, so we can simplify here. So we just get 2 to the 1 is 1. So we get 1 over 1. So that's just 1. X to the 0 is 1. So that becomes 1 plus 2 over 1 factorial is just 2. So 2 times x plus 2 squared is 2 times 2, which is 4. 2 factorial is 2. So that just becomes 2 times 2 over 2, which is just 2. So plus 2x squared. So that's going to be our second degree polynomial. So now we can just do the same thing, similar thing for p sub 3 of x. So we get 2, 0 over 0 factorial, x to the 0, plus 2 to the 1 over 1 factorial, x to the 1, plus 2 squared over 2 factorial, x squared, plus 2 cubed over 3 factorial, x cubed. And one thing you're probably observing is that the first three terms here are just the terms that we saw of p sub 2 of x. So I didn't actually have to write all that out. But that'll help me simplify because I know that the first two, or the 0 first and second degree terms are just going to be 1 plus 2x plus 2x squared. And then that final term here, we can simplify or write 2 cubed is 8 over 3 factorial, x cubed. All right, so now we can do this one more time for p sub 4. And so even we could write out all those terms, or I can just say, I know this is going to be p sub 3. of x plus that fourth degree term. So plus 2 to the 4 over 4 factorial times x to the 4th. So that's going to be 1 plus 2x plus 2x squared plus 8 over 3 factorial x cubed plus 16. 2 to the 4th is 2 times 2 times 2 times 2. So 16 over 4 factorial x to the 4th. All right. And so let's just recall these are the nth degree Taylor series, or Taylor polynomials rather, for our function e to the 2x. So I'm just going to write that down. So what we just computed here, these are the what's called Taylor polynomials for the function f of x equals e to the 2x. And so Taylor polynomials, specifically Taylor polynomials of degree 2, 3, and 4. Okay, cool. So now what we have below here are some pictures of the graphs of these Taylor polynomials compared to our function f of x. So I'm going to highlight our function, or rather I'm going to highlight our Taylor polynomial in green. So we see that our Taylor polynomial here, where'd my green go, is this function here. And our f is this function, this yellow one that's dotted. So I can draw f on all of these pictures. Okay. And then we compare f to the Taylor polynomial of each of those degrees. The red one here. Okay. So what do you notice as you look at these Taylor polynomials compared to the function? Well, one thing you can notice, which we observed in our previous section, is that the larger the degree here, as the degree gets larger, 2, 3, 4, 5, our Taylor polynomial better approximates our function. And so notice that these Taylor polynomials, they're centered at 0. So if we look at x equals 0, then these two functions, or rather the function and the Taylor polynomial, line up exactly. So great, they match at that x equals 0. But then the question is, well, what interval containing 0 do these two functions still align? So we can see for P2, maybe we have a small little interval here. Maybe for P3, we get a little larger. P4, maybe we get to plus or minus like 3/4. And maybe for P5, we get like all the way out from -1 to 1. So the question is, well, then what about as we continue, as n gets larger, so as we look at higher degree Taylor polynomials, what happens to the interval on which the two align? So for which x and n does this happen? So we're going to investigate this in part B.